Hello everyone, I'm Yu Zhongming, a senior student in Tsinghua University. Today I'm going to present our paper about acceleration on GPU. This work guided by Professor Wang Yu is done with Dr. Dai Guohao from Tsinghua University and with Huang Guyue, who is pursuing her PhD degree in UCSB. Our paper is titled Exploiting Online Locality and Reduction Parallelism for Sample-Dense Matrix Multiplication on GPUs. In the following talk, I would use ICCDPre as an abbreviation of sample-dense matrix multiplication. So the outline of the talk will be 4 sections. The first section, I will introduce the background of GPU, usage of ICCDPre, and how to compute ICCDPre, etc. Then I will give the insight of challenges to compute ICCDPre on GPU and illustrate our techniques in the second section. After that, I will demonstrate the detailed analysis based on our techniques. In the last part, I will show our performance compared to the related work, plus implementation in the ML system. ICCDPre has been shown as a key component in the reformulation algorithms of FA, LDA, etc. It also acts as a key role in transformer and backward propagation of graph neural network. It appears as a core operator in DGL and TACO library. After brief introduction of the importance of ICCDPre, we focus on how to compute it. Mathematically, we need 2 dense matrices named A and B and 1 sparse matrix S as input. A has the size of n multiplied k, while B has the size of n multiplied k. To get the output P matrix, we could first apply the dense matrix multiplication of A and the transpose of B, then sample the temporary output by sparse matrix S. In most cases, the density of S is really low, so the problem converts to compute multiple independent dot products. To accelerate ICCDPre on GPU, we should first have a glance at the GPU's architecture. CUDA abstracts parallel programs into blocks of threads. The threads in the block are handed over to the same streaming multiprocessor, abbreviated as SM in the GPU hardware for execution. In this model, the SM schedules threads in groups of 32 parallel threads called warps. The warp scheduler picks an eligible warp and executes all threads in the warp. So next part, we will focus on the challenges of computing ICCDPre on GPU and our techniques to overcome them. The first challenge is brought by poor locality and redundant data loading. Poor locality of sparse data pattern would make traditional tiling method in dense matrix ineffective in ICCDPre. Instead of 2-dimensional tiling, we propose vectorized coarse 1-dimensional tiling, which does not require pre-processing and is adaptive to common data formats such as CSR and COO. This figure shows using tiling in GPU is an important technique to reduce redundant data loading, since each block will request global memory and store data in the L1 cache. Tiling would save SM from reloading data from the global memory. In this method, the input and output of ICCDPre are both implemented with vectorized instruction to increase the utilization of memory bandwidth. So the second challenge of computing ICCDPre on GPU is caused by low utilization of threads in the warp. The red figure shows the reduction tree of computing a dot product in a warp when k is equal to 32. By using GPU intrinsic shuffle down sync, the result from the upper thread ID would be accumulated into the lower thread ID. Finally, we get the dot product from thread 0. As the time goes, the warp would repeat this reduction tree to finish other dot products. This would result in low thread occupancy because there is only one output. We propose integrated interleaving reduction, a method to overcome the above challenge by combining multiple dot products at the same time. As the figure shows, we reorganize the data flow of reduction tree by letting each thread compute partial sum of dot product in the beginning. Then we use shuffle XOR sync to conduct the reduction tree. This time of work could have 4 dot products as output, largely improve the thread occupancy. So, the third challenge of computing SDDMM on GPU is caused by heavy interwarp communication overhead. Restricted by GPU's warp size 32, larger size dot product would lead to interwarp communication. In the previous work of computing vector dot product, atomic add or shared memory are two basic methods to handle communication across warps. However, different from computing single dot product, SDDMM need to aware of computing multiple dot products at the same time. Thus, our experiment found interwarp communication should be eliminated. So, to do this, we propose warp merge tallying, a basic tallying method on dense matrix aware of the GPU warp intrinsic. This method could save loading of sparse data, since each warp only needs to load the row and column of sparse matrix for once. Also, this method would save the shuffle instructions, since we only need to apply reduction tree once in one warp. The following part, I will demonstrate our analysis based on our previous techniques. So, we analyze our experiments on Tesla V100 and NVIDIA RTX 2080. We choose our data set from supersparse matrix collection with at least 10,000 rows and 100,000 non-zeros. We analyze 3 matrices to choose a suitable tiling size. First, we analyze our kernels with different tile size by matrix L2 global load bands, which represents bytes read from L2 cache for misses in L1 cache for global loads. This matrix aims to prove the improvement of the L1 hit rate. First, we analyze our kernels with different tiling size by matrix L2 global load bytes, which represents bytes read from L2 cache for misses in L1 cache for global loads. This matrix aims to prove the improvement of the L1 hit rate. As shown in the figure, the bytes read from L2 for misses drops when the tile size increases from 1 to 16. In theory, expanding the tiling size will make more effective use of data locality and reduce cache misses. However, experiments have shown that continue to increase the tiling size will not achieve better performance. We analyze this phenomenon from another matrix called eligible warps per cycle. It stands for the average number of warps that are eligible to issue per active cycle per SM. Since there are limited workloads in each SM, the eligible warps are fewer in smaller tiling size. However, mapping too many dot products to each SM would cause overloading, reducing the number of eligible warps in each cycle. Here we show the IIR method speedup compared to only using the VCT method. Both kernels are tested under tiling size equal to 16 condition. We select 100 matrices to show the speedup result clearly. Our result shows the geometric mean of speedup by IIR is 2.09 times on RTX 2080 and 1.2 times on Tesla V100. Well, the lower table shows the speedup distribution on the supersparse data set while comparing the WMT method with the atomic add method. Note that the atomic add method also implements VCT and IIR method. In most cases, WMT outweighs the baseline atomic method. Next part, I will show our results compared to the related work and implementation in ML system. We choose 4 typical SDDMM implementation as our baseline. cuSparse is a standard vendor sparse library provided by NVIDIA Corporation. Bitmap is an efficient toolkit for machine learning with several parallel algorithms. Sputnik provides SPMM and SDDMM kernels which are targeted at deep learning application on GPUs. ESPT provides SPMM and SDDMM which based on pre-processing method. Although reordering is an important part of ASPT, we did not include pre-processing time in our evaluation. Our results compared to Kurzbars and BitMac are showed below. When k is equal to 32, we have a speed up about 29.2 times over Kurzbars on average, and 5.2 times over BitMac on average. When k is equal to 1024, many of matrices couldn't be handled by Kurzbars, so we didn't demonstrate this speed up. Compared to Sputnik, when k is equal to 32, we have an average speed up of 167.7 on Tesla V100. Our kernels perform competitively with the approach of ASPT, gaining up of 1.76 times speed up on average without reordering the sparse matrix. Our kernel could accelerate machine learning applications with widely used formats that make it easy to implement in existing frameworks. We embed our SCDM kernel into the ML system called BitMac. We reduce the LDA application time max of 44.8% and reduce the SFA application time max of 30.1% at k equal to 32 condition. Since most of the time is caused by data transmission, our speed up would slow down when k gets larger. This work is included in the DigiSparse project. You could visit our website at digisparse.github.io to browse our code or use our highly efficient kernel. And that's all for my presentation. Thanks for your listening.